Okay, just a quick comment on the upcoming Lagrange multipliers. What you have is you have two functions, and you want to evaluate this function subject to this constraint, that this function equals some constant. Okay, and I tried to draw that and I came up with a bad drawing, but it's like you got two surfaces and you intersect them and you get this constrained hypersurface. Not getting the right words here, but it's kind of this situation, and you get this curve, and on this curve you want to maximize the value of this function. Okay, so I didn't do that very well. I was kind of in a hurry, and we'll do that in some detail, so don't pay too much attention to this example or this picture. Okay, but what we want to do is we want to find the maximum value of this function on that intersection, essentially. Again, we'll flesh out what that means next time. This happens when the gradient of g is parallel to the gradient of f. So you got two functions, their gradients need to be parallel. I wrote something down stupid here because I was thinking perpendicular. There is a way to there's an aspect of this that's perpendicular, so I wrote that down without thinking, so I crossed this out. Okay, so looking for when the gradient of g is parallel to the gradient of f, that means the gradient of g is going to be some constant multiple of the gradient of f. With Lagrange multipliers, we generally use lambda, maybe because lambda is kind of a parallel to the Greek alphabet parallel to L, and Lagrange is a guy who came up with this. I'm not sure that's the reason we use lambda. Lambda is also used for eigenvalues, and there's a similarity there, conceptual similarity. Anyhow, the gradient of g is going to be some constant multiple of the gradient of f, where lambda is some constant. What's that mean? Well, if you have functions of three variables, then the gradient of g is going to have three components. The gradient of f is going to have three components. And if you have this relationship, if the gradient of g is a constant multiple of the gradient of f, then every component has to be the same multiple of the corresponding component of f. Every component of g has to be the same multiple of that component of f. So the gx is that multiple lambda times fx, and gy is that multiple times fy, and gz is that multiple of fc. So we end up, in this case, with three equations and unknowns. And three unknowns, we've got to solve for y. If you're lucky, these equations are linear and they're easy to solve. If you're unlucky, you can't solve them at all. But you have the three simultaneous equations, so you're going to have to exercise your ability to solve simultaneous equations to solve these problems. So really, what you're looking at in the problems that I see in WebAssign, I'll just use this method where you got to do gradient of g is parallel to gradient of f. You get the three equations to solve them, and you do what you do with that solution. With that, I leave you to WebAssign, and we'll work out the geometry of it in more detail next time.